Just say okay and everything is fine. So, yeah, thank you very much. See if I get another security warning here. Yeah, my name is Fabian Karl. I am product manager for PPC's Broadband powerline products, and my presentation is called Broadband for Smart Grids, the need for speed and other things. Some learnings that PPC and soon others also had since 2010. Oh, that's working. So, around 10 years ago, the German regulators were about to define what the German smart metering system is supposed to look like. And if you looked to the European neighbors, they mostly decided to go for narrowband because it was promising high distances and with enough bandwidth for transmitting these little packets of data. In Germany, they took a different approach from the beginning. They decided that the function of the concentrator, which in the other markets is located in the transformer station, should be inside the meter cabinet itself. And the reason why they said, okay, we need broadband, not defining which broadband, is pretty simple. First of all, what do they need with broadband? More or less 1 megabit per second and a latency of around 100 milliseconds at every endpoint. The most important reason for that is security, because only if you have enough bandwidth you can apply state-of-the-art security mechanisms, certificate-based asymmetric encryption, and so on. And we all know we cannot just put one firmware on it and live with it forever. We need to update it. And to update it in time, we need enough bandwidth. That's the most important reason I assume that played a very big role. The other thing is, of course, we also heard that the past 2 days, if we want to have a really detailed grid insight, we need to transmit data more often than once a day, or maybe once every 15 minutes. So also for that, we need enough bandwidth. And we just heard remote controls. They especially rely on low latencies and enough bandwidth for a bidirectional communication. So, what was the decision of many metering operators in Germany? Yeah, it was okay. Let's start with LTE. And why was that? Because it fulfills the regulator's requirement with around 1 megabit per second and around 100 milliseconds. It seems like an easy way because the infrastructure is already there and someone else, the mobile service provider, has to care for it. So not the metering operator himself. And it was also fitting the initial planning of the German smart meter rollout, which was not a full rollout, but only a partial rollout with maybe around 10%. Yeah, the question is, was that really working out as intended? And yeah, it's really suggested here. So it came with a lot of downsides to just rely on LTE. First of all, we have the dependence of the mobile service operators. And since we had the shutdown of the 3G network, we can never be sure when 4G will be shut down. But there's a more technical thing as well, and that's the poor to no reception in the basement, usually also in the metal cabinet, where the smart meter gateway is installed. And if we think about detailed grid insight, we're also talking about increased operational costs with every SIM card and the data volume that is consumed there. So the only logical conclusion for the German DSO is to establish and utilize their own broadband infrastructure. And it will be to no surprise what broadband infrastructure I will be talking about. It is the broadband over power, where they use their own infrastructure and therefore solve the problem of dependency of mobile service providers. Also the lack of LTE reception is no problem because there's always a cable into the basement. And especially in combination with DSL or fiber optics, backbones in substations, the operational costs are near zero. Also, for those places where these don't exist, the operational costs can be lowered, specifically because you do not need so many SIM cards. You only need one for the backbone, and that's it, not 100 for all the smart meter gateways. I have talked about broadband power line generically, but now I will have to be specific because there are so many standards out there. And the reason why PPC has decided to go for IEEE 1901 is because it has some features that are specifically dedicated to smart grids, and I will go through that features now. So one of them is that it supports repeating in general and this multi-hop feature for distance coverage. And I've only got one picture here for that. I mean, it is not really a large distance, but you can see we have like 12 hops back and 13 forth. So we can really increase the distance whenever this is needed. And another very important feature if you want to establish your own network is you do not want to have any manual configuration at all. So the automatic detection of BPL devices and finding the best path to the headend, that is another core feature of 1901 that was very important to us and our customers. And here's just a little animation how it works. So first you install the headends, then you install the repeaters, and from the moment they're installed, they try to find each other, and then they establish the most reliable path. In this example, we have two headends, so also here's some kind of built-in reliability. One of them should go offline, they could all route to the other one. And another thing that is sometimes disregarded is the cell size, because 1901 supports up to 1,000 devices per BPL cell. And although that might seem like a number that is so high you never reach it, we actually observed it in one of our Swiss installations where we had 800 devices in one cell. I mean, this came because of the special structure there with every meter having its own BPL module, so we had many of them. But it is pretty clear that we need this number of devices per cell. And if we take a look at different standards and what they can offer, we see that there's a pretty big difference. So what we used to have in our field is 1901-2010. So the theoretical number of devices is 4,000, with us observing around 800 in the grid. 2020 is like, nearly unlimited devices. While another pretty popular gigabit home networking standard, you can just derive it. Coming from home networking, big cell size is not what they are really planning on. And this is the theoretical value. So we heard today that the HD-PLC supports up to 1,000 devices, which pretty much fits our use cases. So it's pretty, you can be pretty sure that this number is also kind of exaggerated at this point. So the need for speed, that's what I called this presentation. The question is always, okay, the more bandwidth, the better. The typical usage of the frequency is between 1.6 and 28 megahertz. So could go up and use more bandwidth to just create more throughput. But since we are in the grid with power lines having the tendency to attenuate our signal, this is not really a good idea. And therefore, 1901 has a feature for going higher distances by just going the other way. And I know I'm repeating something here because we've heard it a few times and not trying to push it too far, but this is the feature that got us most interested about this new standard. And so what we do is that we have all the carriers, we heard it was 512, not to the whole frequency range, but to the half or even the quarter. And what we do there is we lower the throughput and therefore increase the range. And it is the great strength of the 1901 standard that we already have 2 chip manufacturers which have full interoperability on the PHY and NAC layer already in place. And I'm not exactly sure who had the chance to look at what we have displayed outside. So maybe it will be a reminder, maybe it will be new. But I will just go a little bit in how this works, how we can actually go further by having a lower frequency. So in this very simple example, we have 10 carriers, and to have a stable connection, we need 5 of them. That's the basic idea of all the power line communication. And if we have a channel that looks like this, everything is fine. We have 8 carriers above the theoretical limit, therefore this is a stable connection. But if the cable gets longer, the channels usually look like this. And then we run into a problem, because we only have 4, but we would need 5. And that's the big strength of the new feature of the 1901-2020. By putting all the, in this example, 10 carriers onto half the band, we again have 8 carriers above the limit, and therefore we're okay. But this is all quite theoretical. What is the practical usage of this? The practical usage is that if you're building up your own network infrastructure, in the beginning you can rely on the configuration which just offers the biggest distance, and that is the X4 quarter band configuration. You can easily cover these distances between the street cabinets without the need to place any additional repeaters, for example, in the houses where the meter points are. Once you're installing your smart meter gateways, one by one, or all of them at once, and you need more throughput, or you just want to have more throughput for future use cases, you can switch to, for example, the full band mode, because the distances that you have to cover have shrunk down massively, and therefore you can afford to have a lower range, but with more throughput. And that is what is so exciting about this new feature. So I'm coming to my conclusion. The IEEE 1901 access standard has been designed for smart grid applications from the beginning. It has proven its feasibility since 2010. PPC alone has a lot of devices in the field, many of them running over 10 years without any problem. And it has been substantially upgraded with the introduction of the Broadband, the feature that I just explained in detail. It has a strong ecosystem of chip vendors and OEMs, as we see today, and therefore, in our opinion, is the most future-proof EPL technology for smart grid and smart metering. Thank you very much.
Thank you, Fabian.